Introduction to VXLAN. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this comprehensive presentation, we are going to explore VXLAN, which stands for Virtual Extensible LAN. VXLAN is one of the most important network virtualization technologies used in modern data centers and cloud environments. It has fundamentally changed how we design and operate large-scale network infrastructures. Extended LAN was developed to address the growing limitations of traditional VLAN technology. As data centers grew larger and organizations began adopting cloud computing at scale, the 12-bit VLAN ID field, which provides only 4,094 usable VLANs, became a significant bottleneck. Modern multi-tenant environments require far more network segments to properly isolate workloads and customers from each other. The technology was first defined in RFC 7348, published in August 2014, through a collaborative effort between VMware, Cisco, and other industry leaders. The standard describes VXLAN as a framework for overlaying virtualized Layer 2 networks over Layer 3 infrastructure. This means you can create virtual Layer 2 segments that span across different physical network locations, all while using your existing IP routing infrastructure as the transport mechanism. Let me walk you through the diagram that illustrates the basic VXLAN concept. The diagram shows the fundamental VXLAN architecture with its key components. The original frame represents any standard Ethernet frame that an application or virtual machine generates. This could be any type of traffic including web requests, database queries, or file transfers. This original frame flows into the VXLAN encapsulation process, which is the core mechanism that makes VXLAN work. During encapsulation, the original Ethernet frame gets wrapped with additional headers. The encapsulated packet then enters the IP network, which represents your existing physical network infrastructure running standard IP routing protocols. This is one of VXLAN's greatest strengths because it leverages your existing network investments rather than requiring specialized hardware. Finally, the encapsulated packet reaches the VXLAN decapsulation point, which removes the VXLAN headers and delivers the original frame to its destination as if it had traversed a traditional Layer 2 network. This encapsulation approach means that applications and virtual machines are completely unaware that VXLAN exists. They continue to communicate as if they were on the same physical network segment, even when they are physically located in different data center pods, different buildings, or even different geographical regions. VXLAN Architecture Overview. Now that we understand the problems VXLAN solves, let us examine its architecture in detail. VXLAN introduces several key concepts and components that work together to create scalable network virtualization. The VXLAN Network Identifier, commonly abbreviated as VNI, is the fundamental addressing unit in VXLAN. Unlike the 12-bit VLAN ID, the VNI uses a 24-bit field, which provides over 16 million unique network segments. Specifically, you get 16,777,216 possible VNI values. This massive increase in address space eliminates the scalability concerns that plague traditional VLANs. Each VNI represents an isolated Layer 2 broadcast domain, just like a VLAN, but without the numerical limitations. The VXLAN Tunnel Endpoint, or VTEP, is the device responsible for VXLAN encapsulation and decapsulation. A VTEP has two interfaces conceptually. The first is an uplink interface connected to the transport IP network, which handles the encapsulated VXLAN traffic. The second is one or more downlink interfaces that connect to the local virtual machines or physical servers that participate in VXLAN segments. VTEPs can be implemented in physical network switches, in hypervisor software like VMware vSphere or Linux with Open vSwitch, or in dedicated network appliances. The underlying network refers to the physical IP infrastructure that transports VXLAN encapsulated packets. This network only needs to provide IP connectivity between VTEPs. It does not need to understand anything about VXLAN itself. This separation of concerns is powerful because it means you can build your physical network using any standard IP routing protocol such as OSPF, BGP, or ISIS, and VXLAN will work on top of it. Let me explain the architecture diagram in detail. The diagram shows the layered VXLAN architecture with virtual machines at the foundation. These virtual machines generate and receive network traffic. The virtual machines connect to VTEP1 and VTEP2, representing VXLAN tunnel endpoints at different locations. VTEP1 and VTEP2 both connect to the IP transport network, which is the underlying physical infrastructure. This transport network connects to the overlay network layer, which represents the virtualized layer 2 domain. The overlay network then connects to VNI segments, showing how multiple isolated network segments can exist within the overlay. Each connection in this flow represents a logical relationship between layers of the VXLAN architecture, with physical network infrastructure providing the foundation and virtual network segments existing as abstractions on top. VXLAN Header Deep Dive. Let us examine the VXLAN header in more detail, as this 8-byte structure is what makes VXLAN unique and enables its massive scalability advantages. The VXLAN header format consists of several fields packed into 8 bytes total. The first byte contains 8 flag bits. Of these, only bit 7, counting from 0, is currently defined. This is the I flag, which stands for VNI present. When this bit is set to 1, it indicates that the VNI field contains a valid network identifier. All other flag bits must be set to 0 on transmission and ignored on reception according to the RFC specification. The next 3 bytes, bytes 1 through 3, are reserved fields. These 24 bits must be set to 0 on transmission. They are reserved for potential future extensions to the VXLAN protocol. Receivers must ignore these bytes. Bytes 4 through 6 contain the VNI field. This 24-bit field is the heart of VXLAN's scalability. The VNI identifies which virtual layer 2 network the encapsulated frame belongs to. With 24 bits, you can represent values from 0 to 16,777,215, giving you over 16 million unique network segments. In practice, VNI 0 is typically reserved, leaving you with 16,777,215 usable segments. The final byte, byte 7, is another reserved field. Like the earlier reserved fields, it must be set to 0 on transmission and ignored on reception. The table in the slide provides a detailed breakdown of each field. The flags row shows bits 0 through 7, 1 byte total, with bit 7 being the I flag that indicates VNI validity. The reserved row covers bits 8 through 31, 3 bytes, set to 0 and reserved for future protocol enhancements. The VNI row spans bits 32 through 55, 3 bytes, containing the VXLAN network identifier that enables 16 million plus segments. The final reserved row covers bits 56 through 63, 1 byte, also set to 0 for future use. Understanding this header structure is important for packet analysis and troubleshooting. When capturing VXLAN traffic with tools like Wireshark or TCP dump, you will see these exact fields. The VNI field is particularly important to identify which virtual network a captured packet belongs to. VXLAN control plane options. One of the most important design decisions in any VXLAN deployment is selecting the control plane mechanism. The control plane is responsible for distributing information about which MAC addresses are reachable through which VTEPs, and it determines how broadcast, unknown unicast, and multicast traffic is handled. The first option is multicast-based control plane. In this model, each VNI is mapped to an IP multicast group. When a VTEP needs to send BUM traffic, it sends the encapsulated frame to the multicast group address. All VTEPs that have joined that group receive the traffic. This approach is simple conceptually but requires multicast support throughout your underlying network, which many organizations find operationally challenging. The second option is unicast with ingress replication. In this model, when a VTEP needs to flood traffic, it creates individual copies and sends them directly to each remote VTEP that participates in the same VNI. The VTEP maintains a static list of remote VTEP IP addresses. This approach eliminates the need for multicast in the underlying network but creates more traffic during flooding events because each copy must be sent individually. The third and increasingly popular option is EVPN, which stands for Ethernet VPN. EVPN uses BGP to distribute MAC address reachability information along with other useful data like IP addresses, multi-homing information, and traffic engineering policies. EVPN dramatically reduces flooding because VTEPs learn about remote MAC addresses through BGP updates rather than through data plane learning. This approach also enables advanced features like optimal forwarding, fast convergence, and integration with MPLS networks. VXLAN with multicast control plane. Let us examine the multicast-based control plane in more detail. This was the original method specified in our FC 7348 for handling broadcast, unknown unicast, and multicast traffic in VXLAN networks. In the multicast model, you assign each VNI to an IP multicast group address. For example, VNI 10,000 might be mapped to multicast group 239.1.1.1, while VNI 20,000 is mapped to 239.1.1.2. When a VTEP joins a particular VNI, it also joins the corresponding multicast group using IGMP, the Internet Group Management Protocol. When a VTEP needs to send BUM traffic for a specific VNI, it encapsulates the frame with the destination IP address set to the multicast group for that VNI. The underlying network's multicast routing infrastructure then delivers the packet to all VTEPs that have joined that group. This could use PIM, Protocol Independent Multicast, in either sparse mode or bidirectional mode depending on your network design. The advantage of multicast-based VXLAN is efficiency for flood traffic. The source VTEP sends only one copy of each BUM packet, and the network infrastructure handles replication at optimal points in the topology. This minimizes bandwidth consumption on links closest to the source. However, multicast introduces significant operational complexity. Many organizations lack multicast expertise, and multicast troubleshooting can be challenging. Multicast state must be maintained throughout the network, which consumes memory and processing resources on routers. Additionally, some data center interconnect technologies and cloud provider networks do not support multicast at all. VXLAN with ingress replication. Ingress replication, also called head-end replication, provides an alternative to multicast for handling BUM traffic in VXLAN networks. This approach eliminates the requirement for multicast support in the underlying network. With ingress replication, each VTEP maintains a list of all remote VTEPs that participate in each VNI. When the local VTEP needs to flood traffic, it creates individual unicast copies of the encapsulated frame and sends one copy to each remote VTEP on the list. The replication happens at the source, or ingress, point rather than being distributed throughout the network. The configuration is straightforward. You statically configure each VTEP with the IP addresses of all other VTEPs in the same VNI, or you use a controller-based system that pushes this information to VTEPs automatically. Some implementations also support BGP-based discovery of remote VTEPs, combining unicast replication with dynamic VTEP discovery. The main advantage of ingress replication is simplicity in the underlying network. Your IP infrastructure only needs to support unicast routing, which is standard in every network. There is no multicast state to maintain, no PIM configuration to manage, and no IGMP snooping to troubleshoot. The disadvantage is bandwidth consumption at the source. If you have 100 virtual tunnel endpoints in a VNI and need to flood a frame, the source virtual tunnel endpoint must transmit 100 copies of that frame. This can create significant bandwidth consumption on links close to the source virtual tunnel endpoint. Additionally, the replication processing adds CPU load to the source virtual tunnel endpoint. VXLAN with EVPN control plane. EVPN, which stands for Ethernet VPN, represents the most sophisticated control plane option for VXLAN networks. It has become the de facto standard for enterprise and service provider VXLAN deployments due to its rich feature set and operational benefits. EVPN uses BGP, the Border Gateway Protocol, to distribute MAC and IP address reachability information. Each VTEP establishes BGP peering sessions, either directly with other VTEPs or with ROT reflectors that aggregate and distribute the information. When a VTEP learns a new MAC address locally, it advertises this information via BGP to all peers. Remote VTEPs receive these advertisements and populate their forwarding tables accordingly. This approach dramatically reduces unknown unicast flooding. In traditional VXLAN or bridging environments, when a switch receives a frame for an unknown destination MAC, it must flood the frame to all ports or all VTEPs. With EVPN, the destination MAC is likely already known through BGP, so the frame can be forwarded directly to the correct VTEP without flooding. EVPN also provides several advanced features. ARP suppression allows VTEPs to respond to ARP requests locally based on IP to MAC bindings learned through BGP, reducing broadcast traffic. Multi-homing support enables a server or network segment to connect to multiple VTEPs for redundancy with proper traffic handling. EVPN ROT types support various scenarios including MAC-only ROTs, MAC with IP ROTs, and inclusive multicast ROTs for BUM traffic handling. The diagram illustrates EVPN operation with BGP distribution. The flow starts with VTEP1 learns MAC, representing local MAC address learning. This information flows to BGP ROT reflector, the centralized component that aggregates routing information. From the ROT reflector, the MAC information is advertised to VTEP2 and advertised to VTEP3 simultaneously. Both VTEP2 and VTEP3 then perform populate forwarding table, adding the learned MAC to VTEP mapping to their local databases. This architecture shows how BGP distributes MAC reachability proactively, eliminating the need for data plane learning and flooding for known destinations. EVPN ROT types explained. EVPN defines several ROT types to handle different aspects of MAC and IP address distribution, multi-homing, and multicast traffic. Understanding these ROT types is essential for designing and troubleshooting EVPN-based VXLAN networks. ROT Type 1 is the Ethernet Auto Discovery ROT, abbreviated as EAD. This ROT type serves two primary purposes. First, it enables fast convergence when a multi-home Ethernet segment fails. When a link goes down, the VTEP withdraws its EAD ROT, and all remote VTEPs immediately know to stop sending traffic through that path. Second, it supports aliasing in active-active multi-homing scenarios, allowing remote VTEPs to load balance traffic across multiple attachment points. ROT Type 2 is the MAC/IP advertisement ROT. This is the most commonly used ROT type in VXLAN EVPN deployments. It advertises MAC addresses learned locally, optionally along with their associated IP addresses. When a VTEP learns a new MAC address from a connected host, it generates a Type 2 ROT and advertises it via BGP. Remote VTEPs receive this advertisement and populate their forwarding tables, enabling direct unicast communication without flooding. ROT Type 3 is the Inclusive Multicast Ethernet Tag ROT. This ROT type is used to set up the BUM traffic handling for a VNI. When a VTEP joins a VNI, it advertises a Type 3 ROT indicating how it wants to receive BUM traffic, whether via ingress replication or multicast. Other VTEPs use this information to build their flood lists. ROT Type 4 is the Ethernet segment ROT. This ROT type is used in multi-homing scenarios to elect a designated forwarder for each Ethernet segment. When multiple VTEPs connect to the same multi-home segment, they use Type 4 ROTs to coordinate and prevent duplicate traffic delivery. ROT Type 5 is the IP prefix ROT. This ROT type extends EVPN beyond pure Layer 2 services to support Layer 3 VPN functionality. It advertises IP prefixes for inter-subnet routing within the EVPN fabric, enabling integrated routing and bridging architectures. VXLAN MTU considerations. MTU, which stands for Maximum Transmission Unit, is a critical consideration in any VXLAN deployment. VXLAN encapsulation adds overhead to every packet, and if the underlying network cannot accommodate this additional size, packets will be fragmented or dropped, causing severe performance issues. Let us break down the VXLAN overhead components. The outer Ethernet header adds 14 bytes for the destination MAC, source MAC, and EtherType fields. If VLAN tagging is used on the underlay network, that adds another 4 bytes. The outer IP header contributes 20 bytes for standard IPv4, or 40 bytes if you are using IPv6 in your underlay. The outer UDP header adds 8 bytes containing the source port, destination port, length, and checksum. Finally, the VXLAN header itself is 8 bytes containing the flags, reserved fields, and VNI. Adding these together, the minimum VXLAN overhead is 50 bytes for IP version 4 underlay without VLAN tags. With VLAN tagging, it becomes 54 bytes. For IP version 6 underlay, the overhead is 70 bytes, or 74 bytes with VLAN tagging. This overhead has significant implications. If your original inner frame is 15,100 bytes, which is the standard Ethernet MTU, and you add 50 bytes of VXLAN overhead, the outer packet becomes 1550 bytes. If your underlay network only supports 15,100 byte MTU, this packet cannot be transmitted without fragmentation. There are two approaches to handle this. The first and preferred approach is to enable jumbo frames in your underlay network. Configuring your switches and routers to support 9,000 byte MTU or larger gives you plenty of headroom for VXLAN encapsulation while still allowing standard 1500 byte inner frames. The second approach is to reduce the MTU on your virtual machine interfaces. If you configure virtual machines to use 1450 byte MTU instead of 1500, the encapsulated packets will fit within a standard 1500 byte underlay MTU. However, this approach can impact application performance and requires coordination across all workloads. Cisco NXOS VXLAN configuration. Now let us look at how to configure VXLAN on Cisco Nexus switches running NX-OS. This configuration example demonstrates a basic VXLAN setup with EVPN control plane, which is the recommended approach for production deployments. The first line, feature NXV overlay, enables the NX-OS overlay feature set which is required for VXLAN functionality. Without this feature enabled, the switch cannot perform VXLAN encapsulation or decapsulation. The second line, feature NV overlay, enables the network virtualization overlay feature. This provides the foundational VXLAN capabilities on the Nexus platform. Note that both NXV overlay and NV overlay must be enabled for full VXLAN support. The third line, feature VN segment VLAN based, enables VLAN to VNI mapping capability. This allows you to associate traditional VLANs with VXLAN network identifiers, creating a bridge between your existing VLAN infrastructure and the VXLAN overlay. The fourth line, Feature BGP enables the BGP feature. BGP is essential for EVPN control plane operation because EVPN uses BGP to distribute MAC and IP reachability information between VTEPs. The fifth line, feature PIM, enables protocol-independent multicast. While EVPN can use ingress replication instead of multicast, PIM is still commonly enabled to support certain BUM traffic handling scenarios and provides flexibility in your design. The sixth line, NV overlay EVPN, specifically enables EVPN as the control plane protocol for the VXLAN overlay. This tells the switch to use BGP EVPN for MAC learning and distribution rather than relying solely on data plane learning. Moving to the interface configuration section. Interface NVE1 creates the Network Virtualization Edge interface. This is the logical interface that represents the VTEP on this switch. NVE interfaces are numbered, and NVE1 is the conventional choice for the primary VXLAN interface. The No Shutdown command activates the NVE interface, bringing it into an operational state. Without this command, the interface remains administratively disabled. The Host Reachability Protocol BGP line configures the NVE interface to use BGP EVPN for discovering remote hosts and VTEPs. This is the key setting that integrates EVPN with the VXLAN data plane. The Source Interface Loopback 0 command specifies that Loopback 0 should be used as the source IP address for VXLAN tunnels. Using a loopback interface provides stability because the tunnel source remains consistent regardless of which physical interface traffic traverses. The loopback IP address becomes the VTEP IP address visible to remote peers. The member VNI 100.0.0 line associates VNI 100.0.0 with this NVE interface. This creates the binding between the VXLAN segment identifier and the local VTEP. The Ingress Replication Protocol BGP command, nested under the member VNI configuration, specifies that BUM traffic for this VNI should use ingress replication with the remote VTEP list learned dynamically through BGP EV pages N. This eliminates the need for IP multicast in the underlay network. VXLAN Fabric Architecture. Modern data center networks using VXLAN typically follow a leaf-spine architecture, also known as a close network topology. This design provides predictable latency, high bandwidth, and excellent scalability for east-west traffic patterns common in cloud and virtualized environments. In a VXLAN leaf-spine fabric, the leaf switches serve as the VTEPs. They connect directly to servers, virtual machine hosts, storage systems, and other endpoint devices. Each leaf switch participates in the VXLAN overlay, performing encapsulation when traffic needs to reach a destination on a different leaf and decapsulation when receiving VXLAN traffic from remote leaves. The spine switches provide the interconnection fabric between all leaf switches. In a pure VXLAN deployment, spine switches do not need to understand VXLAN at all. They simply route IP packets between leaf switches based on the outer IP header. This is one of the elegant aspects of VXLAN because your spine layer can be simple, high-performance IP routers without any overlay intelligence. Every leaf switch connects to every spine switch, creating a full mesh of paths at the spine layer. This provides multiple equal-cost paths between any pair of leaf switches, enabling excellent load balancing using ECMP, which stands for Equal Cost Multipath Routing. The UDP source port entropy in VXLAN packets ensures traffic is distributed across all available paths. The underlay network runs a standard IP routing protocol. OSPF, ISIS, or BGP can be used depending on your scale and operational preferences. The underlay only needs to advertise the VTEP loopback addresses so that all VTEPs can reach each other. The overlay network, using EVPN with BGP, operates on top of this IP underlay. EVPN sessions can be established directly between leaf switches in smaller fabrics, or through ROT reflectors in larger deployments. The ROT reflectors are typically hosted on the spine switches or on dedicated control plane nodes. Let me walk through the fabric architecture diagram. The diagram shows a complete leaf spine VXLAN fabric. Spine 1 and Spine 2 represent the spine layer switches providing the interconnection fabric. Both spine switches have full mesh connectivity, with Spine 1 connecting to Leaf 1, Leaf 2, and Leaf 3, and Spine 2 also connecting to Leaf 1, Leaf 2, and Leaf 3. This creates redundant paths between every leaf pair. Leaf 1, Leaf 2, and Leaf 3 are the VTEP switches at the access layer. Each leaf functions as a VXLAN tunnel endpoint. Leaf 1 connects to Server 1 and Server 2, providing network access for these compute resources. Leaf 2 connects to Server 3 and Server 4. Leaf 3 connects to Server 5 and Server 6. The servers represent any endpoint devices including physical servers, virtual machine hosts, or containers. Traffic between Server 1 and Server 5 would flow from Server 1 to Leaf 1, where VXLAN encapsulation occurs. The encapsulated packet routes through either Spine 1 or Spine 2 to Leaf 3, where decapsulation delivers the original frame to Server 5. The return path works similarly, with equal cost multipath potentially selecting a different spine for load balancing. Multi-site VXLAN with EVPN. Extending VXLAN across multiple data center sites enables workload mobility, disaster recovery, and distributed applications. EVPN provides sophisticated capabilities for multi-site deployments, maintaining the benefits of VXLAN while addressing the challenges of geographic distribution. In a multi-site EVPN VXLAN deployment, each site operates as an independent VXLAN fabric with its own leaf spine topology and local EVPN control plane. Sites are interconnected through border leaf switches or border gateways that peer with remote sites over the data center interconnect, commonly abbreviated as DCI. The DCI can use various technologies including dark fiber, carrier Ethernet services, MPLS networks, or even internet-based VPN tunnels. The border devices handle the complexity of connecting sites, including ROT filtering, traffic engineering, and potentially re-encapsulation if the DCI network does not support VXLAN natively. EVPN multi-site introduces the concept of ROT types specifically designed for multi-site operation. Border gateways aggregate ROTs from their local site and advertise summarized information to remote sites. They also handle the re-origination of ROTs, adapting the next hop and other attributes as ROTs cross site boundaries. One key consideration in multi-site deployments is MAC address mobility. When a workload moves between sites, either through live migration or failover, EVPN handles the MAC move gracefully. The new site advertises the MAC address with updated attributes, and remote VTEPs update their forwarding tables accordingly. Sequence numbers in EVPN ROTs help resolve conflicts when the same MAC is momentarily advertised from multiple locations. Another consideration is BUM traffic handling across sites. Flooding broadcast traffic across the DCI can consume significant bandwidth. EVPN provides mechanisms to suppress unnecessary flooding, such as ARP suppression and proxy functions that respond to broadcast queries locally based on information learned through BGP. The diagram depicts a multi-site VXLAN deployment. Site A fabric represents the first data center with its complete leaf spine VXLAN infrastructure. Site A fabric connects to border gateway A, which serves as the interconnection point for this site. Similarly, Site B fabric represents the second data center, connecting to border gateway B. Border gateway A and border gateway B connect through the DCI link, representing the data center interconnect that bridges the two sites. This could be any WAN technology supporting IP connectivity. The DCI link enables BGP EVPN peering between border gateways, allowing MAC and IP ROT exchange between sites. Both Site A fabric and Site B fabric show connectivity to virtual machines in both sites, indicating that workloads can exist in either location and communicate seamlessly across the multi-site fabric. The border gateways handle route aggregation, filtering, and re-origination to optimize traffic flow between sites. VXLAN Packet Capture Analysis. Packet capture analysis is an invaluable skill for VXLAN troubleshooting. When you capture VXLAN traffic with tools like Wireshark or TCP dump, you can see exactly what is happening at each protocol layer and identify misconfigurations or unexpected behavior. Let me walk through the anatomy of a captured VXLAN packet as shown in the slide. The capture shows a complete encapsulated frame with all headers visible. The first line shows the outer Ethernet header. The destination MAC AA:BB:CC:DD:EE:01 belongs to the next hop router or the destination VTEP if they are on the same layer 2 segment. The source MAC 11:22:33:44:55:66 is the local VTEP's interface MAC. The ether type 0x0800 indicates an IPv4 payload follows. The second line shows the outer IP header. The source IP10.1.1.1 is the local VTEP's tunnel source address. The destination IP10.1.1.2 is the remote VTEP's address. The protocol field value 17 indicates UDP. The TTL of 64 is typical for originating packets. If you see unexpectedly low TTL values, it might indicate routing loops or excessive hops in your underlay. The third line shows the outer UDP header. The source port 49152 is a calculated hash value providing entropy for load balancing. Different flows between the same VTEP pair will have different source ports, enabling ECMP distribution across multiple paths. The destination port 4789 is the standard VXLAN port registered with ICANN. The fourth line shows the VXLAN header itself. The flags field beginning with 0x and ending with 08 indicates the I bit is set, meaning the VNI field is valid. This is the expected value for normal VXLAN traffic. The VNI 10,000 identifies which virtual network segment this packet belongs to. Remote VTEPs use this value to determine which local VLAN or bridge domain should receive the decapsulated frame. The fifth line shows the inner Ethernet header, which is the original frame being tunneled. Understanding this packet structure allows you to identify problems such as incorrect VNI assignment, wrong VTEP addresses, MTU issues causing fragmentation, or MAC address learning problems where the inner addresses do not match expected values. VXLAN Best Practices. Let me share the key best practices that will help you design, implement, and operate successful VXLAN deployments. These recommendations come from real-world experience and industry consensus. First, always use EVPN as your control plane unless you have a specific compelling reason not to. EVPN dramatically reduces flooding, provides faster convergence, enables advanced features like multi-homing and ARP suppression, and integrates well with existing BGP infrastructure. Multicast-based VXLAN and static ingress replication are legacy approaches that should be avoided in new deployments. Second, enable jumbo frames throughout your underlay network. Configure at least 90 00-byte MTU on all interfaces in the VXLAN transport path. This provides ample headroom for VXLAN overhead while still supporting standard 15 00-byte inner frames. Document your MTU configuration and verify it during deployment testing. Third, design your underlay network for simplicity and stability. Use a leaf spine topology with layer 3 routing at every hop. Use a proven routing protocol like OSPF, ISIS, or BGP. Keep the underlay configuration simple because its only job is to provide IP connectivity between VTEPs. Do not add unnecessary features or complexity to the underlay. Fourth, implement proper monitoring and visibility. Deploy tools that can see both underlay and overlay status. Monitor VTEP health, BGP session state, EVPN route counts, and VNI statistics. Implement logging and alerting for control plane events. Consider using flow telemetry to understand traffic patterns. Fifth, plan your VNI allocation strategy carefully. Use a consistent numbering scheme that makes VNIs easy to identify and manage. Consider aligning VNI numbers with VLAN IDs where practical for operational simplicity. Document your VNI assignments and maintain a central registry. Sixth, test thoroughly before production deployment. Verify encapsulation and decapsulation with packet captures. Test convergence scenarios including link failures, device failures, and control plane disruptions. Validate performance under load to ensure your design meets throughput requirements. The summary diagram presents key best practices as a mind map structure. Best practices is the central concept. From this center, control plane branches to use EVPN for production, emphasizing the recommended control plane choice. MTU branches to enable jumbo frames 9000+, highlighting infrastructure requirements. Underlay branches to keep it simple with layer 3 spine, reinforcing design principles. Monitoring branches to track both layers, emphasizing visibility needs. VNI planning branches to consistent numbering scheme, addressing operational organization. Testing branches to validate before production, stressing the importance of thorough testing. Each branch represents a critical area for VXLAN deployment success. VXLAN security considerations. Security is a critical aspect of any VXLAN deployment that requires careful planning and implementation. While VXLAN provides network isolation through VNI segmentation, it does not inherently provide encryption or strong authentication. Understanding these security characteristics helps you design appropriate protections. VXLAN encapsulation itself does not encrypt traffic. The inner Ethernet frame travels through the underlay network wrapped in VXLAN headers, but the payload remains readable by anyone who can capture packets on the underlay. In environments where traffic confidentiality is required, you need to implement additional encryption mechanisms. IPsec can be used to encrypt VXLAN traffic between VTEPs. By establishing IPsec tunnels over the underlay network, all VXLAN encapsulated traffic benefits from encryption and authentication. Some platforms support native integration of IPsec with VXLAN, while others require configuring IPsec separately on the tunnel endpoints. MACsec, which stands for Media Access Control Security, provides encryption at layer 2. When implemented on the physical links between switches, MACsec encrypts all traffic including VXLAN packets. This approach protects against eavesdropping on individual network segments but requires MACsec support on all intermediate devices. VNI isolation provides logical separation between tenants or security zones, but this isolation depends on correct configuration. A misconfigured VTEP could potentially bridge traffic between VNIs that should be isolated. Proper change control, configuration validation, and monitoring are essential to maintain isolation integrity. Access control should be implemented at multiple layers. Firewall rules can restrict which traffic is allowed to enter or leave VXLAN segments. Microsegmentation solutions can enforce policies between individual workloads within the same VNI. Network access control can authenticate devices before allowing them to join VXLAN segments. The diagram illustrates the VXLAN security architecture with multiple protection layers. VXLAN traffic is the starting point representing encapsulated overlay traffic. This traffic can flow through IPsec encryption, which provides tunnel-level protection and connects to encrypted transport. Alternatively, traffic can flow through MACsec on links, providing hop-by-hop encryption. The VXLAN traffic also connects to VNI isolation, which provides logical separation between tenant segments. Additionally, firewall and access control lists connect to policy enforcement, implementing traffic filtering. All these security measures feed into the secure VXLAN fabric, representing the protected network environment where multiple security controls work together. VXLAN performance optimization. Achieving optimal performance in VLAN networks requires attention to several factors including hardware offload capabilities, proper sizing, and configuration tuning. Let me walk through the key optimization strategies. Hardware offload is one of the most impactful optimizations. Modern network interface cards and switch application-specific integrated circuits can perform VXLAN encapsulation and decapsulation in hardware, eliminating CPU overhead. When using software VTEPs like Linux or hypervisor-based implementations, look for network interface controllers that support VXLAN offload. The network interface controller handles adding and removing VXLAN headers, calculates checksums, and can even perform inner packet segmentation. TCP segmentation offload, known as TSO, allows the NIC to segment large TCP packets. With proper VXLAN offload support, TSO can work with encapsulated traffic, letting applications send large buffers while the NIC handles segmentation after VXLAN encapsulation. This dramatically reduces CPU utilization for bulk data transfers. Large receive offload, or LRO, works in the opposite direction, aggregating multiple received packets into larger buffers before passing them to the CPU. Generic receive offload, GRO, provides similar functionality in software. These features reduce interrupt overhead and improve throughput for received traffic. Receive side scaling, abbreviated RSS, distributes incoming packet processing across multiple CPU cores. For VXLAN traffic, RSS should hash on the inner packet headers to ensure traffic from different flows is distributed across cores. Some NICs require explicit configuration to enable inner header hashing for tunneled traffic. ECMP load balancing in the underlay network distributes VXLAN traffic across multiple paths. The UDP source port entropy in VXLAN packets enables effective load distribution. Ensure your underlay routing is configured for ECMP and that all available paths are being utilized. Arista EOS VXLAN configuration. Arista network switches running EOS provide robust VXLAN support with EVPN control plane integration. Let me walk through the configuration for setting up VXLAN on an Arista switch. The first section configures the VXLAN interface. The interface VXLAN1 command enters the configuration mode for the VXLAN interface, which is the VTEP interface on Arista platforms. The VXLAN source interface loopback0 command specifies that the loopback0 interface's IP address should be used as the VTEP IP address. This loopback must be advertised in the underlay routing protocol so remote VTEPs can reach it. The VXLAN UDP port 4789 command explicitly sets the UDP destination port for VXLAN. While 4789 is the default and IANA assigned port, specifying it explicitly ensures consistency and makes the configuration self-documenting. The VXLAN VLAN 100 VNI 10100 command creates a mapping between VLAN 100 and VNI 10100. Traffic from local ports in VLAN 100 will be encapsulated with VNI 10100 when sent through the VXLAN overlay. This mapping allows you to maintain existing VLAN numbering schemes while using different VNI values as needed. The VXLAN learn restrict any command configures the switch to only learn MAC addresses through the control plane, not through data plane flooding. This is important for EVPN deployments where MAC learning happens via BGP rather than traditional flood and learn behavior. The second section configures BGP for EV pages in. The router BGP 65001 command enters BGP configuration mode with autonomous system number 65001. The neighbor 10.0.0.1 remote AS 65001 command establishes a BGP peering session with a root reflector or another VTEP at IP address 10.0.0.1. Since both are in AS 65001, This is an IBGP session. The neighbor 10.0.0.1 send community extended command enables sending BGP extended communities to this neighbor. Extended communities are essential for EVPN because they carry route targets and other EVPN-specific information. The address family EVPN command enters the EVPN address family configuration. Within this context, neighbor 10.0.0.1 activate enables EVPN route exchange with the specified neighbor. Without activation, the BGP session would be established but would not exchange EVPN routes. Juniper QFX VXLAN configuration. Juniper QFX series switches provide comprehensive VXLAN support with EVPN integration. The Junos configuration style differs from other vendors but provides the same functionality. Let me walk through the key configuration elements. The first section configures the VTEP source interface. The set interface's low 0 unit 0 family INET address 10.1.1.1/32 command configures the loopback interface with an IP address that will serve as the VTEP identifier. This address must be reachable by all remote VTEPs through the underlay network. The next section configures the VXLAN tunnel endpoint. The set switch options VTEP source interface low 0.0 command specifies that the loopback interface low 0.0 should be used as the source for VXLAN tunnels. This is equivalent to the source interface configuration on other platforms. The set switch options route distinguisher 10.1.1.1:1 command configures the route distinguisher for EVPN. The route distinguisher makes EVPN routes unique when multiple VTEPs advertise the same MAC addresses in different contexts. Using the VTEP IP as part of the route distinguisher is a common convention. The set switch options V or F target 65001 100 command sets the default route target for EVPN routes. Route targets control which routes are imported and exported between VTEPs, enabling flexible topology designs. The VLAN and VNI configuration section uses set VLAN's VLAN 100 VLAN ID 100 to create VLAN 100. The set VLAN's VLAN 100 VXLAN VNI 10100 command associates this VLAN with VNI 10100, creating the bridge domain to overlay mapping. The set VLAN's VLAN 100 VXLAN ingress node replication command enables ingress replication for BUM traffic on this VLAN. With EVPN, the remote VTEP list is learned dynamically through BGP rather than being statically configured. The BGP configuration section establishes EVPN peering. The set protocol's BGP group EVPN overlay type internal command creates an internal BGP group for EVPN sessions. The set protocol's BGP group EVPN overlay local address 10.1.1.1 command specifies the local IP address for BGP sessions, typically the VTEP loopback. The set protocol's BGP group EVPN overlay family EVPN signaling command enables the EVPN address family for this BGP group. Finally, set protocol's BGP group EVPN overlay neighbor 10.1.1.2 specifies the BGP neighbor IP address. VXLAN versus Geneve comparison. Geneve, which stands for Generic Network Virtualization Encapsulation, is a newer overlay protocol that addresses some limitations of VXLAN. Understanding the differences helps you choose the right technology for your environment and plan for future evolution. VXLAN has a fixed 8-byte header with a 24-bit VNI field and limited flag bits. This simplicity is both a strength and a limitation. The fixed format ensures interoperability between implementations but provides no room for protocol extensions or carrying additional metadata. Geneve uses a variable length header that can carry type length value options. The base header is 8 bytes, similar to VXLAN, but can be extended with TLV options to carry arbitrary metadata. This extensibility allows Geneve to support future requirements without protocol version changes. Both protocols use UDP encapsulation. VXLAN uses destination port 4789, while Geneve uses port 6081. Both benefit from UDP source port entropy for ECMP load balancing in the underlay network. The VNI field in Geneva is also 24 bits, providing the same 16 million segment scalability as VXLAN. From a scale perspective, neither protocol has an advantage in terms of segment count. Geneve has become the preferred encapsulation for some newer platforms. VMware NSX-T uses Geneve rather than VXLAN. Open Virtual Network, or OVN, the control plane for Open vSwitch, supports Geneve as its primary encapsulation. Microsoft Azure uses Geneve for its virtual networking. VXLAN remains widely deployed and well supported across physical network equipment. Most enterprise switch vendors have mature VXLAN implementations with EVPN integration. For physical network infrastructure, VXLAN with EVPN is the current industry standard. The table in the slide provides a detailed comparison across multiple dimensions. VXLAN in public cloud environments. Major public cloud providers use VXLAN and similar overlay technologies to deliver their virtual networking services. Understanding how cloud providers implement network virtualization helps you design hybrid and multi-cloud architectures. Amazon Web Services uses a proprietary encapsulation for their virtual private cloud networking, but the concepts are similar to VXLAN. Each VPC operates as an isolated network with its own IP address space. AWS handles all the overlay complexity transparently, so customers interact with high-level constructs like subnets, security groups, and route tables rather than VTEPs and VNIs. Microsoft Azure uses Geneva for its virtual network implementation. Azure VNets provide isolated network segments similar to VXLAN VNIs. Azure also offers VXLAN-based solutions through services like Azure Virtual WAN and ExpressRoute, enabling connectivity between on-premises VXLAN fabrics and Azure cloud resources. Google CP Platform uses Andromeda, their software-defined networking stack, which implements overlay networking with concepts similar to VXLAN. Google CP VPC networks span globally by default, with Google's network fabric handling the overlay transparently. For hybrid connectivity, Google CP supports Cloud Interconnect and VPN solutions that can integrate with on-premises VXLAN environments. Hybrid cloud architectures often need to bridge between on-premises VXLAN fabrics and cloud virtual networks. This typically involves VPN or dedicated connectivity services that translate between your VXLAN segments and the cloud provider's virtual networking constructs. Some cloud providers offer direct VXLAN support through specialized connectivity options. Migrating from VLAN to VXLAN. Migrating an existing VLAN-based network to VXLAN requires careful planning and typically follows a phased approach. Let me walk through the key stages and considerations for a successful migration. The first phase is assessment and planning. Document your existing VLAN topology, including all VLANs in use, their purposes, and which devices and applications depend on them. Identify your VNI numbering scheme. Many organizations simply add a prefix to existing VLAN numbers, so VLAN 100 becomes VNI 10100. Map out which network segments will migrate first, typically starting with less critical workloads. The second phase is infrastructure preparation. Ensure your network hardware supports VXLAN, upgrading software or replacing equipment if necessary. Configure your underlay network with appropriate IP addressing, routing protocols, and MTU settings. Deploy your EVPN control plane infrastructure including route reflectors if needed. Verify underlay connectivity between all planned VTEP locations. The third phase is gateway deployment. Configure VXLAN gateways that bridge between your existing VLAN infrastructure and the new VXLAN overlay. These gateways allow gradual migration by enabling communication between devices that have migrated to VXLAN and devices still on traditional VLANs. The gateway extends the same broadcast domain across both technologies. The fourth phase is workload migration. Begin moving workloads to the VXLAN network, starting with your designated pilot group. Monitor for connectivity issues, performance problems, or application errors. Document any issues and their resolutions. Gradually expand to additional workloads as confidence grows, using the gateways to maintain communication throughout the transition. The fifth phase is gateway removal. As workload migration completes for each segment, you can decommission the bridging gateways and the legacy VLAN infrastructure. Verify all communication paths work correctly through the VXLAN overlay before removing gateway connectivity. This phase may take considerable time as you wait for all dependent systems to migrate. VXLAN automation with Ansible. Automating VXLAN configuration with tools like Ansible improves consistency, reduces human error, and enables rapid deployment and changes. Let me walk through an Ansible playbook that configures VXLAN on network devices. The playbook begins with the YAML document separator and the name field identifying this playbook as VXLAN EVPN configuration. The hosts field specifies leaf switches as the target inventory group, meaning this playbook will run against all devices defined in that group. The gather facts field set to no disables automatic fact collection since network devices often do not support standard fact gathering. The var section defines variables used throughout the playbook. The VTEP_source_interface variable is set to loopback 0, indicating which interface provides the VTEP IP address. The VXLAN_VNI variable is set to 10,100. Specifying the VNI to configure. The VLAN ID variable is set to 100, representing the local VLAN mapped to this VNI. The BGP_ASN variable is set to 65,001, defining the BGP autonomous system number. The ROT_reflector variable is set to 10.0.0.1, specifying the BGP ROT reflector peer address. The task section contains the actual configuration operations. The first task is named Enable VXLAN Features. It uses the NXOS_feature module, which is specific to Cisco NXOS devices. The feature parameter specifies NV overlay as the feature to enable. The state parameter set to enabled ensures the feature is activated. The second task, Configure NVE interface, uses the NXOS_VXLAN_VTEP module. The interface parameter specifies NVE1 as the NVE interface name. The source_interface parameter uses the VTEP_source_interface variable to set loopback 0 as the tunnel source. The host_reachability_protocol parameter is set to BGP, enabling EVPN-based host discovery. The third task, Configure VNI member, uses the NXOS_VXLAN_VTEP_VNI module. The interface parameter again specifies NVE1. The VNI parameter uses the VXLAN_VNI variable to configure VNI 10100. The ingress replication parameter set to BGP enables dynamic floodlist learning through EVPN. The fourth task, Configure BGP EVPN neighbor, uses the NXOS_BGP_neighbor module. VXLAN summary and key takeaways. Let us recap the essential concepts and key takeaways from this comprehensive VXLAN presentation. Understanding these fundamentals will help you design, deploy, and operate successful VXLAN networks. VXLAN solves the fundamental scalability problem of traditional VLANs. The 24-bit VNI provides over 16 million network segments compared to just 4,094 VLANs. This massive increase in segment capacity enables modern multi-tenant data centers, cloud environments, and large enterprise networks to scale without constraint. The overlay and underlay separation is a key architectural principle. VXLAN creates virtual Layer 2 networks that operate independently of the physical network topology. Your underlay network only needs to provide IP connectivity between VTEPs. This separation simplifies physical network design while providing unlimited flexibility in virtual network topology. EVPN has become the standard control plane for production VXLAN deployments. Using BGP to distribute MAC and IP reachability information dramatically reduces flooding, improves convergence, and enables advanced features like multi-homing and distributed gateways. If you are deploying new VXLAN infrastructure, EVPN should be your default choice. MTU planning is critical and often overlooked. VXLAN adds at least 50 bytes of overhead to every packet. Enable jumbo frames throughout your underlay network to avoid fragmentation issues. Test MTU end-to-end before production deployment. Leaf spine architecture with Layer 3 routing provides the ideal underlay design. This topology delivers predictable latency, high bandwidth, and excellent scalability. Keep the underlay simple and let the VXLAN overlay handle network virtualization complexity. Multi-vendor interoperability is achievable with standards-based implementations. VXLAN with EVPN is supported across Cisco, Arista, Juniper, and other major vendors. While configuration syntax differs, the underlying protocols enable interoperability in mixed vendor environments. Security requires additional measures beyond VXLAN itself. Implement IPsec or MACsec for traffic encryption if confidentiality is required. Use firewalls and microsegmentation for traffic control. Monitor your VXLAN fabric for security events and anomalies. Automation is essential for managing VXLAN at scale. Tools like Extensible enable consistent configuration across large numbers of devices. Infrastructure as a service practices improve reliability and enable rapid changes. The diagram summarizes the key VXLAN concepts as a comprehensive mind map. Thank you for your attendance. Please consider subscribing to the channel and liking this video.